E1 by real quickly moving through it. First thing we'll talk about is kind of our curved arrows. We've got our reaction drawn up above. Because it's E1, we're going to form a carbocation, so the leaving group leaves first. Okay. Then in E1, typically the way we lose that next hydrogen is the heat vibrates the bond enough that the electrons come down to form the pi bond, and we'd have H plus kind of chilling on the outside. Okay, and that's typically what we reference. You will usually see some form of solvent. That solvent almost always has a pair of electrons, and that solvent can actually act as a weak base to pick up that hydrogen, so that we have something actually doing that chemical reaction instead of just saying heat vibrates it off. Okay. When we're talking about these, you'll sometimes hear them referenced as beta eliminations, because the hydrogen that is removed is beta to the alpha, where our alpha is our leaving group, the carbon where our leaving group is located. The problem with most of our eliminations, or not necessarily a problem, complexity, maybe complexity is the right word, is that there's usually multiple beta positions. Deciding which hydrogen to remove is going to come down to the stability of the pi bond that is formed. So if I removed from the beta shown in orange, I'd get the double bond there. So one of the conversations that we encounter is stability of double bonds. Double bonds that are more substituted are more stable. And so when we run our elimination, we want to remove hydrogens from the position that would generate the most substituted double bond. That's an awful lot of words, and people tend to trip up and not like that. So what you can reference instead is remove hydrogens from the position that had the fewest hydrogens. Okay, some people refer to this as the poor get poorer. Okay, if we count hydrogens as currency, there are 3 hydrogens at the orange beta position. There are 2 hydrogens at the green beta position. So the poor gets poorer, you're going to remove your hydrogens from the place that had the fewest hydrogens. Okay? Less a fan of that because it removes some of the chemical understanding, but we're in that gray area for this class. Okay? The big summaries that kind of come out of that, unfortunately I've got to delete everything now. We've got our substrate. Okay, since we're forming a stable carbocation, anything that can go through to make the carbocation stable will speed up the E1 reaction, make it more likely to happen. Your leaving group needs to be good, per usual. Okay, base is our subtle change. Here we're usually using something that is weak, and you'll almost always see a reference to heat. Okay. So heat we showed could be that heat. It could also be written as that delta. I don't think I would use it, but you could see it also as an actual temperature value that's greater than 25 degrees Celsius. That's technically adding heat. The solvent is technically polar protic because you're looking at stabilizing the carbocation. Again, it's misleading, so I would hesitate or caution you on overusing the solvent to interpret eliminations. Okay. Your regiochemistry, technically when I say mainly trans, we're referring to the stereochemistry, not the regiochemistry. The regiochemistry is forming that more substituted double bond. Okay. This was observed a long time ago by a Russian called Zaitsev, or his last name was Zaitsev, I believe. There's a whole bunch of different spellings out there because apparently no one knows how to write Russian names. So just be aware of that. I've seen it with a Z and I've seen it with an S as well, along with multiple different variations of the F, and I think I've seen a Y get dropped in there too. Okay, but it's all referring to the same thing. Benefit isn't necessarily a benefit. As we talked about, rearrangements are possible because you have a carbocation. Okay. The biggest issue that you guys are going to be concerned about, though, is that it directly competes with SN1. All of those conditions, one for one, match the conditions for an SN1 reaction. Okay. So if you see something that looks like SN1, that's likely to encounter E1 products as well. The one differentiating factor is what? Heat. Okay, so if you're seeing heat, that's okay. You can start saying it's doing the E1 elimination. Okay, if you don't see heat, you should be leaning towards the substitution mechanism. Okay. E2, just like the SN2, has it all happen at once. So we need our leaving group to leave at the same time we form the pi bond. Okay. That pi bond encounters the same kind of issues that we saw with the E1. We're again removing beta hydrogens, and we now have these options that we could remove from either of those locations. Okay. In SN2, what was its big thing that made it different from an SN1? I know, I shifted gears real fast there.
I just got really confused.
Okay, so ignore elimination for the moment. We have SN1 versus SN2.
2 steps.
2 steps, fair. What else is a differentiator? Backside attack, yeah.
No.
There's no carbocation. The nucleophile. Your nucleophile has to be strong. That's why it's coming in from the backside. You need a strong nucleophile, so you're looking at something that's negative. In the case of the E2, you're still looking at something that's negative, except now that negative isn't trying to react as a nucleophile, it's trying to react as a base to remove that hydrogen. Why does it need to be strong? Well, the leaving group won't leave until it's forced off. It's forced off by the electrons being from, or by the hydrogen having been removed by the base. Okay? So you need a strong base to force that process to occur. Okay? Similar to the E1, we do tend to favor more substituted alkenes. So given a choice, we get the more substituted alkene. Okay? But an interesting dynamic comes out. Because this is happening at the exact same instant, it is possible that we are not given a choice. Okay? And what encounters out of this is the same concept as that we get for the SN2 backside attack. If we go through and draw this structure a little bit differently, everybody's going to hate this. What am I drawing? The Newman projection. If we look at our leaving group there, okay, there's our hydrogen. This is our orange CH3 out there. I don't care about that one. Oops, it's not going to be over there. Why would I put that black CH3 where I did? Because initially I had drawn it here, right? Yeah. Okay, why is it better to have that black CH3 on the far right?
So
it's not eclipse, it's still staggered.
I said so it's not
It's still staggered.
What?
Say it again. It's the type of staggered. If we put the CH3 here to that left, that's a gauche interaction. We don't like that. If we put the CH3 on the opposite side, that's now anti. Okay? So there's our green hydrogens that we could go through and eliminate. Okay? When we go through and do this, we get the exact same kind of considerations that we get with the SN2. It's a backside attack. What we're saying is that as this leaving group leaves, the electrons, so there's that bond, there's that leaving group leaving, the electrons that come in to make the pi bond must come from the back side of that bond. Which means when I look at the Newman projection in this drawing, which hydrogen is removed?
The one that's closer to the leaving group?
Okay. So now if we color it, it helps blue versus green. Which hydrogen is eliminated? So my base comes in with that negative charge. Does it go blue or does it go green? (50-50). What's the worst that could happen?
Blue?
Okay, blue. What was the key word that we needed to know with SN2?
Backside.
Backside attack. Where is the backside of this bond? Is it here? No. If it's not right there, then what does that mean about blue?
No.
That's a bad idea. Where's the backside of that leaving group bond? Okay? The green one's on the backside. Okay? So our base has to come in to remove that hydrogen. That configuration to allow the elimination is known as our anti-configuration. When we're referencing the leaving group and the hydrogen, their relationship are anti to each other. That is a requirement for our E2 reaction. What you'll hear reference to is something known as anti-periplanar. Okay? I think they aren't just calling it anti because you're doing a chemical reaction and that's why they add extra words. Okay? But what we're saying is that that hydrogen has to be anti to it. Okay? Why is this important? Okay? Well, if we looked at that starting structure, to get these products, we have to have the hydrogen align. Which of these two products, left or right, comes from that green hydrogen being removed?
Right? Left?
Yes, one of those.
Okay. I did it.
Okay? Here's kind of a cheat. Okay? This is what's happening in the mechanism, right? That's how it looks. But what happens is we delete the leaving group and we delete the hydrogen. We've now made the double bond, which means we can't do any rotations. If I now take this molecule and turn it to the side, what happens?
The CH3s are opposite.
The CH3s are on opposite sides. Which of my products has the CH3s aimed opposite directions? The right one. Okay? How do I get the left one?
If they're on the same.
The CH3 would have to be on the same side. True. How do I get it? What has to happen?
What do you mean?
Because according to this, we just said we need the hydrogen to be anti to the leaving group. If I remove this hydrogen for the leaving group, I get the trans product. How do I get the cis product? What has to happen? There's the right idea. We're rotating. Okay, if we take the back structure and I rotate it, okay, the blue hydrogen, so I'm going to rotate downwards, the blue hydrogen is now the green hydrogen. Okay, that CH3 is now my green hydrogen. And that blue hydrogen becomes my CH3. Did that kind of fast? Did you see all that? Okay, now the blue hydrogen is in that anti-alignment. Now I can run the elimination. Okay, so those arrows are now kind of ignore the color. Our base can come in, remove, the electrons swing in to make the double bond. Okay, now where are the CH3s? They're on the same side, that's producing that product. Okay, why would I expect the trans over the cis?
Because
There's a gauche interaction in the transition to make the cis product. That gauche interaction destabilizes that Newman projection, which means the CH3 would tend to rotate into the anti-CH3 so that my green hydrogen allows the elimination and I get the trans. Okay. When we talked about E1, we could say either one formed because we're having the hydrogens react to form the carbocation. There is a slight energetic difference because the trans is more stable, but here it's not just a cis versus trans, it's actually going all the way back to when the reaction actually occurs that dictates it. So what does this mean for us? In E2, almost exclusively, we'll push towards the trans and not the cis. So you get a better favoring for the cis product than you do for E1. Or sorry, the trans product than you get for E1. Okay, kind of, sort of. Another complication can come into play. Never mind. Let's leave it at that. Questions about that? I can tell you really didn't like that. Are you okay with it? Okay. So cool. We predict our products. God, do I want to bring in that other complication? I don't think I want to bring in the other complication.
Can we do another example?
Yes, and oh, wow, that was weird. Yes and no. I generally say no because I'm horrible at making things up on the spot. But let's see what I can come up with. Did we say what pH meant?
Yeah,
So we're good. I can write pH.
the ring thing.
Yeah. Okay. We probably have not said what ET means, have we?
Extraterrestrial.
Fair play. Let's try OChem. What do you think ET stands for? As a hint, this could also mean ME. Ethyl. Okay. So it's a little bit easier to write ET than to do, I mean, if we just do line angles, we could just draw the line, it's not a big deal. Okay, but if you're going to draw in all the atoms, that becomes obnoxious. Okay, so I am actually technically, with this example, going to make it problematic. Okay, so what product do we expect out of this?
Confused on where the base takes the hydrogen from.
So our leaving group should leave, but then our base needs to come in and remove a hydrogen, right? It removes the hydrogen from the beta position. Where's our beta position? Well, if this was alpha, that could be beta. Do we have any hydrogens at the beta position?
No,
No, which means
they can't do
I can't do the elimination there.
that. You have to do another thing. Another thing.
Do I have another beta position? Yeah, that was a CH3. That CH3 has hydrogens. I could have the base come in, remove those electrons, and form the double bond. Okay. Do I need to worry about the whole Newman projection deal? Hopefully not. Okay, well, but why? And since nothing happened at the other spots, I can do those as identical.
Because you're not adding the pi bond in the middle.
Ooh. You're not adding the pi bond in the middle, which is technically why we don't have to worry about it, but you can do better than that. Just saying a not in the middle isn't quite good enough. Make it more organic chemistry.
I don't even know how you show any projection with one end that has a pi bond on it, like the front, and let's say the back has.
So there, if we're looking at the Newman projection in this particular molecule, okay, do you like the leaving group in front or in back? Front? Okay. So our eyeball is kind of back here, looking at this. I'll put the leaving group straight up. And we'll address why I'm not worrying about stereochemistry there in a second. Okay, so then in behind, we have that carbon. Is that red, orange okay? I think that's okay. The 3 hydrogens. So what's our base doing? Our base is coming in, removing that hydrogen, the electrons sweep up to make the double bond, to make the leaving group leave.
So weird looking to me.
Does that help?
Yes.
Okay.
So the question was, why wouldn't we do it?
Yep. Why am I not concerned about this whole anti-periplanar stuff?
Because there's,
Wait, because you started to say something.
Oh, because it's not like anti or anything like that.
It's still anti.
Well,
there's not two CH3s
Yeah.
that could interact. Whether it be gauche or
That's getting at the better statement. There's not two hydrogens that are interacting from the same carbon. So we don't have this gauche versus anti thing that we had for the previous case. Did you all like looking at Newman projections? No. What was the repercussion of gauche versus anti?
anti's better.
What was the repercussion? When I had them gauche, what happened with my product?
It was less likely it was better.
Because we were looking at cis versus trans. Okay? When we have a system of cis versus trans, that's where we have to be really careful with the Newman projections and making sure we've got our lowest energy gauche and all that fun stuff. Okay? That's where we have to stress. Why do I not have to stress here? Can this double bond do cis trans? It can't. So it's not so much that it's in the middle. I mean, you're kind of right. Okay? But we could create a system where it is in the middle, but it still doesn't have cis trans. Okay? And I wouldn't care then either. It's because this double bond doesn't have a cis trans isomer. I don't care. I don't need to draw this all out because I can infinitely rotate that orange carbon and back to put a hydrogen anti, and it doesn't change the output of my answer. It only matters if I have to worry about this cis trans thing. Does that make sense?
Yeah.
Okay. So in this case, we don't form a super stable double bond. But why not? I didn't have a choice. It's the only place that I could form the elimination. Okay? What we have to be careful of is to acknowledge where our hydrogens are. And yeah, in this case, I set it up in such a case where the example didn't have a hydrogen where we wanted it to be. Chemistry doesn't care where you want it to be. It cares where it is. So you have to change your viewpoint to align to that. All right? And if you don't like these examples, blame Alina. You're welcome. Oh, this is a really rude one. I apologize. I actually genuinely apologize for this one. What's our product? Right? Leaving group leaves. Our base comes in with the electrons. Oh yeah, you ta-da, we get our answer. Where does the hydrogen need to be? Anti. It needs to be the complete opposite direction of where the leaving group is. Where's the leaving group aimed right now? Up and to the right in the plane of the molecule. Which of those three bonds is directly opposite that leaving group? The CH3, which means it's not anti. My hydrogen is not in the anti configuration. I would have to do a bond rotation to bring the hydrogen into alignment so that it could do the elimination. Okay? So if I do that bond rotation, okay, and this becomes kind of fun in the drawing, okay, as we rotate this around, so we've got our phenyl kind of aimed up here, and what I'm going to do is start rotating it that direction, away from us, because I need this hydrogen that's away from you to come out towards you. Does that make sense? So as I rotate, the hydrogen needs to come out to be in the plane. So my hydrogen's now here. That phenyl that was kind of at us is now rotated to the back. And my CH3 is now rotated up. Do I need to write CH3, or are we okay? Is that just a wedge? Okay. Now when we go through and do the oh man, stupid red bond I should have erased already. Now when I go through and do the elimination, whoop, now we're in the anti-alignment. how should I draw the product? No idea. I've gone through things where I've filled the whole thing up and somehow just accidentally just deleted it all. It's soul crushing. Okay. There's our double bond. The double bond has to have 4 things coming off of it. The question now becomes, what are those 4 things? Right? We've got 2 halves. We'll call it the green half and we'll call it the orange half. So the green half has a CH3 and an H that need to go onto it. Yep. And the orange half has a pH and a CH3. How do I put it together?
The green, the CH3
Okay, so you want to put the CH3 here and the H there. Ultimately, once you've done, it actually doesn't matter where you put one side. Once one side is defined, now the other side becomes really important. Don't screw it up.
CH3 is opposite of pH. On the same side? Same side.
Wait, take a pick. What do you want CH3 to be?
I meant same side. It might be wrong, yeah.
Okay, so we're going to say CH3 there, and you're putting the pH there.
Yeah.
Does everybody agree with her? Or does somebody want to throw her under the bus and be like, no, she's doing something wrong? What do you think?
No, I thought, looking at the wedges and the dash, that was determined.
The wedges and the dashes are going to help you actually answer this. So when we go through and look, I'm perfectly okay with your green side. Wedge, CH3, you're going to put at kind of the lower, fine. Hydrogen needs to be the opposite direction, fine. But the CH3 was wedged. What is that CH3?
Wedge.
Which means they are aimed the same direction. Did you aim them the same direction?
No.
No. CH3 belongs down here. pH belongs up there. The pH is dashed going away. What is the hydrogen? Dashed going away. Okay? So that puts them in the same orientation relative to the pi bond. Now you've got your answer. So you can use those wedges and dashes to help navigate it. What else could you do? Newman projections. Yeah. Do you want to look at the Newman projection? You're a horrible person. Okay. What do we call it? We call the left. Green. I want my. Did we put leaving? We put the leaving group in front, didn't we?
Yeah.
There's my eyeball. That's a horrible eyeball. Oh my god. Let's just do this. Eye. Okay. So there's our eye in front. My leaving group is above my eye. Right? So straight up. Left and right where my eye is coming in. The CH3 is on what side of my eye? The left. Hydrogen's on the right. We go to the back, carbon. Now an orange in the back. Okay. Sorry, I thought I did something weird. Okay. If we're looking at my eye here, the hydrogen's in the plane, just like the leaving group is, but it's in the plane down. If my leaving group is in the plane up, my hydrogen needs to be straight down. Okay. Where is this CH3? Okay. It's on what side of my eye? If my eye's coming in this way, it sees this wedge coming in on my left, which means this CH3 is also on the left. But it's on the left where? Up. Which is why I think you were flipping them before, is you were placing where the atom was, not recognizing the three-dimensional shape. So if my eye's coming in, there's my CH3. I shouldn't be standing in front of this. How do I do this? There we go. My eye's coming in. I see the CH3 on the left, hydrogen on the right, leaving group straight up. Is everybody good with that one? Okay. Nailing down the other end can be harder. That's why I would start with something that I know already. I've already defined. The hydrogen is in the plane. My leaving group is in the plane. They're aimed direct opposite directions. So I would drop in that hydrogen. Okay. The next part is as I'm looking down that CH3 is coming out wedged. If I turn my eye, where is it? It's on my left-hand side and it's upwards. Okay. That really leaves only one space for that phenyl. Okay. But if we see the phenyl, it's kind of down, officially it's up there. Okay. And when I turn, it's now coming to the right. Okay. The exact orientation at which you draw those technically doesn't matter, but does it change your interpretation? I drew this phenyl kind of downward, which then meant when I looked at it, I was looking at it this way, and when I turned, that's not where it's aimed, right? Okay. If I drew it more appropriately, the phenyl should actually be upwards, okay, and backwards, so that when I turn, I can see it more cleanly there. This is why it can become really, really important to draw your structures to the appropriate three-dimensionality. If you don't have them drawn properly, it becomes much harder to overall interpret, okay? It's still possible once you nail down a frame of reference. And that's why I started with that leaving group in the plane. Okay? The phenyl, and then doing the hydrogen, and then saying, well, the wedge, okay, going the opposite direction, it needs to align that way. So now when I go through and do my elimination, what happens? Here's where my pi bond forms. Where's my CH3s? Well, they're on the same side. Are they on the same side? Yeah. Phenyl and hydrogen on the same side. Does that help to visualize? Which is unfortunate, because it usually does really help. It just sucks to draw Newman projections. Okay? Make sense? So I just hit you with 2 examples. You feel a little better? Okay. This is a much harder one because we had to do some rotations, because what's drawn here, right, wasn't what we were given. We had to do a rotation to get it into alignment. Make sense? Okay. So what does that mean as we put this all together? Okay, well, our substrate. Okay, the substrate is where our leaving group is located. Right, it's usually referencing just that carbon, so I don't want to color in the rest. Okay, what do we want for that substrate? That's where the pi bond forms, but this is prior to the substrate actually forming. Okay, our hydrogen needs to come in from the backside. What happens if I put a bunch of carbons out here? It's hard for the electrons from the hydrogen to swing in because there's an electron repulsion, which means the substrate should be less substituted. We don't want a bunch of carbons on that spot. We want that to be substituted with hydrogens. That would be pushing our zeroary, our primary, secondary, okay, with tertiary being last. Which is interesting because if we think back to what we did for the SN2, okay, what we were referencing is substitution patterns, backside attack. So our substrate tends to focus on making the more stable pi bond, but at the same time, and stable pi bond's dangerous on this, we will favor our primary over our secondary, and then tertiary we won't do, or sorry, no, I flipped this. SN2 has a different issue. I moved the wrong direction there. Okay, it is making the stable pi bond, because that backside of that bond really isn't all that impacted because you're talking about the hydrogens. Whoops. The chemistry of your hydrogen coming in. Okay, that reaction. That's relatively close-knit and tight. Changing the identity of these pieces isn't going to do much. Okay? But what will do much is if the pi bond I get is more substituted. Because if it's more substituted, it's a more stable double bond. Okay? What does that mean for us? If I want more substituted, what kind of leaving group or what kind of substrate would I expect? I know it's a hard question. Okay. I want that pi bond, the forming pi bond, to have as many non-hydrogen things on it as possible. Which means when I look where that leaving group is located, what identity should I have there? Do I want hydrogens or carbons? I want carbons. Because that's resulting in a more substituted pi bond. If I put those as carbons, it's now tri-substituted. If those were hydrogens, it's mono-substituted. Does that make sense?
Yeah.
Okay. So what does that mean for your substrate? If you wanted those to be carbons, qualify, name that substrate. Tertiary is actually going to be better than secondary and better than primary. Okay? Those are going to be better systems because it's generating a more stable double bond. Why do we get this kind of inverse in it? In substitution, if we looked at an energy diagram, it works something along these lines. Our nucleophile was higher in energy than our leaving group, which meant when we look at the energetics of the reaction, our products were lower in energy than our reactants. This was substitution. Take a look at an elimination. Okay, we'll have our base, which is fine. Okay, and we've got our alkyl structure, but now what do we end with?
Something higher.
We end with a pi bond, which is higher in energy where we start than where we started. That difference in energetics for our overall reaction causes some secondary issues to come about. One of those being that we want the most stable pi bond. We want a tertiary pi bond or a tertiary substrate because we get a more substituted pi bond at the end. And that's because the energetic difference of our reactions. Kind of, sort of? Okay. Leaving group always needs to be good, kind of misleading. What about the base? Okay. The base is what drives this reaction. Okay. That base must be strong so it can pull that hydrogen off so that the electrons can come in and force the leaving group out. Okay. So I need the strongest possible base I can get. Okay. Why is that potentially problematic? If I have a strong species, that could also favor SN2. So if I see a negatively charged thing, how do I know it's acting as a base versus a nucleophile? Well, do I know the difference between a base and a nucleophile? If yes, I've got a good solid hint that I'm setting up and doing an elimination versus a substitution. If I don't know the difference between bases and nucleophiles, am I going to be stuck? Yes. Okay? So, for instance, if we look at just the negative species, so let's not actually mislead and say it's necessarily acting as a base. I look at a negative species that is this. Would I expect that to act more like a base or more like a nucleophile?
Base.
That should be a base because
It's large and it's donating to hydrogen.
it's large. Okay? We don't necessarily know that it's donating to hydrogen necessarily yet. You're right.
It's large.
Okay? Because it could just as easily be doing the substitution. Okay? I wanted E is the word I wanted there. Because it is large, that's difficult for it to get in to do a backside attack to kick out the leaving group. Instead, what it does is it removes the hydrogens, because the hydrogens were on the outside of the molecule. Let's not do I minus. Let's do Cl minus. Should be a little bit more within your wheelhouse. This one ends up being a nucleophile and not a base. Why? Chloride's pretty dang big.
I don't know, it's on the second row, it makes it seem smaller.
In the previous case, it was the oxygen reacting and it had a tail that was big. Chlorine is significantly larger than the oxygen right out of the gate. So the immediate size is significantly larger. Didn't sound like it broke. hopefully. Hopefully I didn't just jinx you. Okay. What if chlorine acted as a base? What would happen?
It would take hydrogen,
It would accept a hydrogen to make what?
HCl.
What do you know about HCl?
Just one acid.
What do strong acids do? What is the definition of a strong acid?
It accepts H plus acceptor.
It donates H plus immediately. So chloride will never act as a base because what does it form? A strong acid that immediately goes back to forming chloride and H plus. So our chloride, bromide, and iodide are all the only species that will act as nucleophiles, not as bases. Because if they act as a base, they make a strong acid. Strong acids aren't stable, they immediately revert backwards. Okay? So that's one that's worth memorizing. Okay? Our halogens are nucleophiles, not bases. Okay? Another one worth memorizing is this one up here that you called out as a base, T-butoxide. Okay, you could make the argument that you don't need to memorize that one if you understand that it's large. Great, fully accept. Okay. Last one, OH minus.
That's a base.
Sodium hydroxide is indeed a base. Yes, that's not what I asked.
What do you mean? What do you mean? Is it a level?
Can it act as a nucleophile?
Yeah.
It's not a question of does it act as a base, it's looking at base or nucleophile. And if all you're saying, oh, it's base, are you saying it can't act as a nucleophile?
It can't just.
It can. It's small. Hydroxide sucks. Because what can hydroxide do? It can act as both. It is both a good nucleophile and a good base. So hydroxide is one of those misleading things. Right? Or you could look at, oh, it's this great thing because it can do everything. But most people don't like that when it comes to things having to do with chemistry. Okay? So hydroxide is small, so it can act as a nucleophile. It's also really good at accepting hydrogens, so it can act as a base. Hydroxide is a double dagger, it can do both things. Okay? Why could the top one? That's still a negative oxygen. Negative oxygen. Why was that one not a strong base? Or sorry, strong nucleophile.
It can't go in the
It was sterically, the electrons around it prevented it from acting as a nucleophile. So it comes down to boiling down to the difference between a nucleophile and a base. Okay? That is not always a clear-cut line, but that's something that you're responsible for having some familiarity with. Okay? That some familiarity is largely going to center on those three things. Okay? Both nucleophile or base. Okay? And it's those conditions that force those.
How do you know when OH is nucleophile?
How do you know when OH minus is acting as a nucleophile or acting as a base? That's a really good question, and you're not going to like the answer. Is OH minus acting as a nucleophile or as a base?
Are we considering the product?
Are they written there?
Yeah.
Yes,
But it's acting as a base.
it's acting as a base. OH minus acting as a nucleophile or a base. OH minus acting as a nucleophile or as a base. Now I don't know. Does that suck? Yeah, it sucks a lot. Okay, let's do one more thing. Is it acting as a nucleophile or as a base?
Are we still considering the heat?
Fair point.
Oh.
No hints. Is that a guess? Do you have one?
Maybe.
Okay, you think it acts as a nucleophile. If it acts as a nucleophile, what mechanism are you running? Okay, you'd be running an SN if the OH minus acted as a nucleophile. Okay, SN2 if it acting as a nucleophile. When I say SN2, you say backside attack. And what does that then mean you should reference as far as your substrate? I want a small substrate. Do better. That's good, but we want to be able to qualify our small substrate. Say it again. It's the name we can associate with our substrates. Zeroary, primary, secondary, tertiary. So I want a small substrate. You want zeroary would be faster than primary, would be faster than secondary, and tertiary doesn't happen. So we said, oh, it's SN2. I think it can act as a nucleophile. We remember, we think its substitution is acting as a nucleophile. We'd have to say it was SN2 because it's a strong nucleophile. If I have a strong nucleophile, that suggests backside attack, which means the substrate I want is zeroary, primary, secondary, not tertiary. What substrate do I have? Tertiary, which means it's not SN. It has to run E2, which means the hydroxide is acting as a base. Holy sweet monkeys. Okay? All of those thought processes, you went through number one. So don't be like, oh my God, this is impossible, I can't do it. You did it. Okay? And you did it. You have to start that process and start working through those things. Okay? With practice, you pick up the fluidity to be able to channel through those things fairly fast. But you have to build that practice. Make sense? Good job. Okay. Solvent. This is where the solvent is really, really, really misleading. And I keep erasing that thing. So the solvent here, okay, is almost always nearly protic. Okay. Problem with the E2, we're not forming a carbocation. So why is it protic? Because similar to the SN2, we actually prefer aprotic. But you'll almost always see it as protic. Well, what was a good base? Sodium hydroxide, right? How do I get sodium hydroxide to dissolve in this reaction? I usually take sodium metal and I add it to water to make sodium hydroxide. You mean the solvent is water? Yes. Okay? It's a natural repercussion of trying to make a strong base. Okay? Other common bases, okay? Almost all of them go back to a negative oxygen. We can use OCH3 minus. How did you get it to be negatively charged oxygen? You took methanol, OCH3, and you added sodium metal to it. What does the sodium metal do? It removes the hydrogen, giving me the negative charge. Am I in a protic solvent? Yes. Okay. So the solvent is very, very misleading there. It should preference aprotic, polar aprotic, but almost universally you'll see it as protic. Okay. So just be careful with the solvent. I will try my best to not put questions out there like that, but I don't know what you see in the future. Okay. Next system with our regiochemistry. Okay. Regiochemistry and ultimately our complications. What are we referencing there? How did we figure out what hydrogen was removed? Newman projections. So it's all dictated based off of the alignment of the leaving group and the hydrogen. Okay? If you have lots of hydrogens, then it generally doesn't matter. Okay? If you have very few hydrogens, then you're going to need to be very, very careful to ensure that your hydrogen is anti to the leaving group when you make the double bond, and that when you've brought in that alignment, you now see all those pieces. which could mean you're good at looking at the line wedge, or you need to draw Newman projections. If you feel you need to draw Newman projections, that's okay. Okay. My argument on an exam, if you feel like you need to draw Newman projections, is flip and skip the question because it's going to take you forever to draw it. Okay. Write Newman on the exam so you have a note, go through the rest of the exam, come back to it, draw out your Newman projections so that you can then get the answer down. Make sense? Okay. Even if you don't feel you have to do Newman, it's still interpreting the wedges and dashes. That can be very tricky to manipulate. That, again, might just make sense to leave it alone, come back to it when you have time, if you have time. Okay? The big word that comes out of that is the anti-periplanar, or I've also seen anti-coplanar. They're all referencing the same thing. Okay? We do tend to favor Zaitsev product, which means more substituted. Okay? More substituted and more stable. I should say more stable instead of more substituted. Okay, so trans is favored over cis. But again, it's heavily dictated by where the leaving group and the hydrogen are located. So you can get cis products if that's the only hydrogen you can remove. You can get less substituted products if that's the only hydrogen you can remove. So be careful on focusing in on where that hydrogen is located to ensure that you're getting the proper alignment. Okay. There is this added complication, what's known as the Hoffman elimination. Okay, with that example that I showed where we had two different things, we'll just call them R's. Okay, and we eliminated it out this way. Okay, and we formed a very unsubstituted double bond. Okay, that's kind of what Hoffman's talking about, except what Hoffman is actually saying this scenario. I have two hydrogens to choose from. I have the red versus the orange. Okay? According to what we just talked about with our eliminations, which hydrogen should I remove? Red or orange? The red, because it results in the more substituted double bond. Okay? Hoffman ended up going through, because they're named after people, Hoffman went through and he changed some of the experimental conditions, and he noted that he could get the orange in preference. Okay? How do you go through and do that? Well, what does your base have to do? The base has to remove that hydrogen, right? If that hydrogen is near very, very large R groups, can the base get into the hydrogen very easily? No. Okay? So if those groups are big, that can limit the red hydrogen from reacting. Add on top of it, to make it extra sure that that red base can't make it in there, make the red base really, really big. So if all of those things come into consideration, what happens is that your base can't get to the hydrogen it wants to, and it instead removes the hydrogen that's more accessible. Okay? It's a very limited situation. It typically happens at this level when we're talking about that base, because it's very bulky. That can favor the less substituted double bond formation. Okay? But there are some other conditions that go with it. Again, I don't know that I really want to test on that because we're drilling into kind of nuances of it. Again, it's more just you're aware of it. If you're looking at other videos, you'll hear reference absolutely to Zaitsev. You'll absolutely hear reference to Hoffman eliminations. Okay, the Hoffman elimination is a very special circumstance that forces that to happen. Okay, if we now look at our big summary, E1 versus E2, okay, when we're looking at our substrate, we just want stable products for the most part. The E1's a little bit more dependent on the cation stability because the cation's the first thing that comes out of the gate. Okay, but for the most part, you're trying to get more substituted double bonds. When we come to the negatively charged species, E2 favors a strong base, okay, because we're trying to force the reaction to happen. E1, I don't care what the base is. Why? The slow step was forming the carbocation. The base happens afterwards. So it's usually a weak base. Leaving group is standard across the board. The substrate pattern becomes a little bit more interesting when we look at E2 and E1. they both preference tertiary substrates because those tertiary substrates result in more stable pi bonds. Okay? This should actually scream as a good thing. Okay? What happens if I see, and actually this shouldn't even be on here. Why should the CH3X not be on here for an elimination?
It's not possible.
Why is it not possible?
Keep a methyl group, where would you put the ion?
If those are all hydrogens, okay, remember it's called beta elimination. That carbon is alpha. I need another carbon to be beta to have the hydrogen on it. Okay? So what does that mean for us? What happens if you see a zero-area substrate?
It's not elimination.
It's not elimination. Do better.
It's
It's substitution. Okay? Do even better.
It's,
It has to be SN2. Okay? So we can kind of stack that information. Solvent, polar product for E1, because it's not important for E2, I don't think it's even really relevant to memorize it for E1 either. Okay? Like I said, generally there'll be polar product for both of those. Stereochemistry, this anti-orientation is a little bit vague. What is the anti-orientation in reference to?
the leaving group and the hydrogen.
It's the hydrogen and the leaving group need to be in an anti-orientation. Why do we not need an anti-orientation for E1? It forms the carbocation. Why does that matter?
Because there's no backside attack.
It is still technically doing a backside attack. But I could have my hydrogen drop the electrons in there. If I did a bond rotation, I could put the hydrogen down here, and it could still drop the electrons into the exact same orbital. Okay? The p orbital has electrons both above and below with our carbocation. That's why I don't have to worry about anti-orientation, because it has both options. It can go in from the top or the bottom and still be anti. Okay? We tend to see the trans as the most likely for the E1. When we're looking at the E2, our stereochemistry gets a bit dodgy because it's so heavily dependent on the anti-orientation. Okay? So you can get cis or trans. You can also potentially get less substituted. Okay? If we look at our regiochemistry, we again tend to favor Zaitsev, the most substituted double bond. Again, the E2 heavily dependent on our anti-orientation. Kind of, sorta? Okay. Hooray! So, what does this actually get us to? This now gets us to this table, which is in a textbook that you guys don't have access to, so we'll just show up my modified version of it. Okay. What you should be going through and doing, or the last kind of stage in this, okay, some of the questions are, which mechanism are you doing? Which of these substitution mechanisms are you doing? SN1 or SN2? So now you're just concerned about the differences between SN1 and SN2. I can then ask, which one is it, E1 or E2? Fair. The end goal is, here's a reaction. What do I expect? Okay? So in that case, it could be SN1, it could be SN2, it could be E1, it could be E2. Because they all have the same conditions, I have to be able to nuance each of those systems out of it. Okay? This table should look kind of familiar. This table should look almost identical to all the other summary tables we've done. Okay? And what you're effectively doing is asking yourself a question about it. So we start here. Do I have a strong nucleophile? So I could look up here. What's my nucleophile? Do better than NABR. Say it again. Do better than BR. Yes. BR minus, I accept that. Ideally bromide. The sodium we can immediately lop off because it's a spectator ion, so we can ignore that. We're looking at BR minus. Okay? So recognizing NABR is okay. Recognizing BR is okay. Recognizing BR minus is even better, because what do we see? It's negative, which means it's strong. Did SN1 want a strong mechanism or strong nucleophile?
No.
No. So yes, SN2. Okay? It's not applicable for the eliminations. Why not? They use bases. What's the next question? Is it a strong base? Okay, again, not applicable, okay, for our substitutions. Okay, but we could go back and say it was Br minus a strong base. It is strong. Is it a base? No, that's the one that if it reacted as a base, it forms HBr. HBr is a strong acid. That's not going to happen, which means no's. So for me, I wouldn't write anything in those. If I'm saying no's, I'm not going to write. Okay, leaving group. Leaving group is on the chart. I should still delete it, and it shouldn't be that high up. But do we have a leaving group? Yes. Okay, so why should I delete it? Because do you need a leaving group for SN1? Yes. Do you need a leaving group for SN2? If it's going to get counted for all of them, that's pretty useless. Okay. Substrate. Where's the substrate? Okay, the carbon structure. We do have to be a little bit careful with that. Is this a carbon structure? Yes. Is that a substrate? No, why not? What are you looking for when you're looking at the substrate? It's not just carbons.
That's what I was gonna say. I was thinking about tertiary.
That's the next part. That's classifying it once we've identified it. We need a leaving group. Chlorine's a good leaving group. I don't have a good leaving group in that molecule. So while it has carbons, it doesn't have a good leaving group. That's not going to be the substrate. Okay? So what I'm looking for when I look at my reaction is to identify those pieces. Okay? So my chlorine's my leaving group. The substrate classification I care about. What kind of classification is that? Secondary. This gets obnoxious because which mechanism favors secondary? They all do. Okay. Substrate should still be included on it. It just happened to pick the unlucky substrate of secondary where they're all favored. Solvent. DMSO. Okay. This is an example thing, so I wouldn't ask it like this on the exam, or if I did, you should call attention to it because you are not expected to know those symbols. You're expected to know the structure. DMSO is a structure. Is that? What is the solvent classification?
Polar aprotic.
Polar aprotic. Which mechanism favors polar aprotic? SN2. Okay. The eliminations were questionable at best, okay, and almost always protic solvents. Okay. The SN1 was for sure protic. Okay. Do we have heat mentioned? No. So what does that suggest?
It's not elimination.
Okay, it's not elimination. I would actually probably write no's for that, okay, because there it's the lack of the presence of heat. You could probably go through and say yeses here. Okay, so now what can we do? Total it up. For the SN1, I have 3 yeses. For the SN2, I have 1, 2, 3, 4, 5 yeses. For the E, I would almost say 1, because I had 2 yeses and then an absolute no. That's a bad idea, right? Okay, for the E2, depending on how you wanted to count it again, 1. So what mechanism do you think happens? SN2. Why is that important? Now you need to predict the product. What's the product?
Carbon chain with the eon. And it's real nice.
Yeah. If you haven't noticed that already, organic chemists are notoriously bad at balancing equations. Does everybody want to agree with her? What's that? Okay? We have to be careful with stereochemistry. It's fine. Yeah, you ran a substitution. Did you run an SN2 substitution? Okay, the SN2 means you understand the complications of that SN2. When I say SN2, you say backside attack. If my leaving group is wedged, my nucleophile needs to be dashed. Okay? Get the idea? Okay. So it's lots of kind of intricate moving pieces, and you're now trying to come up with an organizational system behind it. For the one person that took 152, it's like ice charts. Okay, this is kind of like an ice table. Okay, if you haven't, don't worry about it if you didn't take it. It's not necessary as a technique to solve questions, but it really helps to kind of organize and structure your thought process. Make sense? Okay. This table, I think, does kind of the big summary job, but I will say that I've got a couple other slides that kind of add some text things for it. Okay. Strength determines your order. Okay. Order is a fancy term. Don't stress too much about it. I'll define it here in a second. So strong nucleophiles or bases prefer bimolecular two-type reactions. So if I see something that's strong, that's SN2 or E2 because they're strong. Okay? It doesn't tell me I favor SN2. It just tells 2 type. So it could be either SN or E. Okay? The next part, how do you differentiate between SN and E? Well, nucleophiles is our substitution. They're donating electrons to things on the inside. Because of that, we want very little sterics. We want small things. Bases donate electrons to the outside. So sterics is kind of a moot issue. If I want it to act exclusively as a base, what I'll do is make it big. Okay? That's where we're getting T-butoxide. Okay? Again, with the symbols, don't stress too much about it. That carbon is a tertiary carbon because it's connected to 3 other carbons. That's the T, tert. The bute is because there's 4 carbons there. Okay? And that's where T-butoxide is coming from. If you're like, that's not how we learn nomenclature, you're right, it isn't. Don't worry about it, just pretend. Okay? DBN and DBU are much larger kind of extended structures. Much more steric hindrance than we get for T-butoxide, but ultimately the same thing. You end up with a negatively charged species that can remove those hydrogens. If we're looking at nucleophiles, the examples I provided here are, again, the halogens, because those are the ones that act exclusively as nucleophiles and not as bases. Okay? Almost everything else spans the gambit between both. Okay? And how would you know which one was supposed to be the important one? Look at your other bits of information to help you decide I should be doing substitution or elimination. Or if it comes out as a tie, what do you do? No, if I total it up and I say I get 4 for SN2 and 4 for E2, I'm going to say 1 and 1. What do I do?
For heat?
Still tie.
Look for base?
It's a tie. No.
Oh, it can do both.
Do both.
There we go.
Okay? So when it hits a tie, do both. Okay? That's how you break the tie, unfortunately, is do both. Okay? That can be misleading because what could happen is maybe you just misinterpreted something and it shouldn't have been both. Okay? But there will be scenarios where you get both. Usually it's SN1 and E1, not the 2s. Because of heat and for the for something else, the word escapes me. Okay. So strength of the nucleophiles, bulky favors elimination because you're looking at those being as bases. Substrate structure, your primary halides are SN2. So if you look through your ranking system, generally speaking, primary is high priority for SN2, it's low priority for E2, and it doesn't work for either SN1 or E1. So if you're seeing a primary halide, it's usually okay to call it SN2. We can kind of cheat and just jump to that. Got to be a little bit careful because you could have a base in there. Okay? Secondary halides suck. Hope you find something else that gets you some information. Tertiary is another big one that sucks because you get a mixture of everything, except SN2. Okay? Your solvent effects, your products favor SN1, aproducts SN2, high temperatures favor elimination, and that's it. Okay? So at this point, it now just comes down to practicing questions. Okay? For me personally, I know you're copying stuff. It's going to come back to these tables. There's one for SN1 and one for SN2. Okay? And really getting familiar with what those things mean. You have to apply them. Rote memorization of this table is useless if you can't apply it out. Okay? This does provide that summary for the stereochemistry and regiochemistry on it, so that helps. Okay? After that, what you're doing is taking what you've memorized and now setting up a kind of a flow chart to compare your way through. Okay? After that, these provide some language, if you were trying to copy that down, some language to kind of support what those patterns meant. That can be easier than the structures we looked at. It's just kind of up to you. Make sense? Okay. We don't have a whole lot of time left. Do you have immediate questions? Okay, so what I wanted to do real quickly is look at these practice documents, which were supposed to be real short, and they ended up turning into these big long things just because it was easier for me to do that. Okay? So for that very first question, that's not really big. Why won't you let me zoom in more? Jerk. Okay. Which of the following steps could be found in an SN1 mechanism? Do you care about forming a pi bond? Why not?
It's substitution.
Pi bond is elimination. I'm being asked about substitution. So we talked through this saying all these things are things you need to be concerned about. That doesn't mean you're being asked all those things every single time. I can just look at an SN1 and say, give me some information within this. Give me some information within the SN2. So don't panic and go, oh, there's way too much stuff. Start working your way through for the individual channels. You may struggle with putting it all together at the end. That's okay. That's not the whole test. Okay? What I want to look at is at each of those individual sections. Make sense? Okay, so when I say SN1, you say carbocation. So if you looked at this question, you might immediately ignore this one. Okay? We could draw arrows that didn't involve a carbocation though. Okay? But we might immediately ignore that and shift to these ones where we have positive charges. Okay? And now we could go through and evaluate what's happening in those. In 2, what are we doing? What does that arrow show the motion of? Electrons from where to where? To the bond. That's an elimination. Not right. Okay? What's the next one show? Bromine as a negative, sharing with a positive. Like that's the legitimate arrow. That looks an awful lot like the substitution mechanism. Okay? Ideally, you'd remember that from the beginning, and that's a coordination mechanism, which happens to be step 2 of an SN1 mechanism. Right? What happens in the next one? Br minus is attacking H. That should already be like, that's a little weird, because what would you make? You would make HBr a strong acid. We shouldn't be doing that. Okay? But then the electrons in that bond go to making a bond, i.e. Okay? What's happening in the last one?
Where are the electrons coming from?
That response is exactly what I want to hear. Well, like, what? That, I don't understand. Yeah, because you understand how electrons move. I guarantee you that is shown in second semester OChem. Someone will draw that and say this is how things are going because they haven't learned how to move electrons. Your response to that should entirely be, what the hell is going on with that? Okay? That is the appropriate response. Okay? I should never have an arrow start at a positive charge. That's just nonsensical. Okay? I did eliminate one right out of the gate, so we could double back just to make sure what's happening there. We're at least starting the arrow where we have electrons, the bond, okay? And we're taking those electrons and moving them to the carbon. Why does that not make sense?
Electronegativity.
Iodine is more electronegative than carbon. We would expect the electrons to go the other direction. That also doesn't make sense. So not only does it not have the carbocation, it also doesn't make sense because the electrons are going the wrong way. Kind of, sort of?
Yep, yep.
I think that was a good note to end on.